The year is 1600, and somewhere in the mountains of Japan, a master craftsman is about to create something that will outlive empires. Not a sword, not a piece of pottery, but a bronze temple bell that will ring for centuries. What you're about to witness is a process so complex, so precise, that one tiny mistake could turn months of work into expensive scrap metal. And the crazy part? They're doing all of this with nothing but fire, clay, and knowledge passed down through generations. You might think making a bell is simple. Just pour some metal into a bell-shaped mold and call it a day, right? Wrong. Creating a temple bell that produces the perfect tone requires an understanding of metallurgy, acoustics, and craftsmanship that would impress modern engineers. These Japanese bell makers weren't just metalworkers. They were part scientist, part artist, and part magician. The process they perfected was so sophisticated that even today, with all our modern technology, we still struggle to replicate the pure, haunting sound of these ancient bells. Here's something that will blow your mind. A single temple bell could take up to 6 months to complete from start to finish. 6 months for one bell. That's longer than it takes to make a car today. And we're talking about craftsmen working with basic tools in an era when electricity was still centuries away. The dedication and skill required was absolutely insane, but the results speak for themselves. Some of these bells are still ringing today, more than 400 years later, with the same crystal clear tone they had the day they were first struck. Before we dive deep into this incredible journey, make sure you hit that subscribe button and give this video a like. I promise you're about to learn things about bell making that will change how you hear every church bell, temple gong, or wind chime for the rest of your life. And when we're done, drop a comment letting me know what part of this process surprised you most. Because trust me, there are going to be several moments where you'll question everything you thought you knew about metalworking. The whole process began with something deceptively simple, a wooden model. But this wasn't just any piece of wood carved into a bell shape. Master bell makers spent weeks creating these patterns, measuring and adjusting every curve, every thickness variation, every decorative element. The wooden model had to be absolutely perfect because every imperfection would be copied into the final bronze bell. One small bump or dent in the wood could ruin the bell's tone forever. These wooden models were works of art in themselves. The craftsmen carved intricate patterns, religious inscriptions, and decorative bands that would eventually appear on the finished bell. The most skilled pattern makers could create models so detailed that you could read individual characters in the inscriptions just by running your fingers over the wood. But here's the fascinating part. They had to carve everything in reverse and account for the shrinkage that would happen when the bronze cooled. It was like creating a 3-dimensional mirror image while doing complex math in your head. The real magic started when they used this wooden model to create the mold. This wasn't your typical pottery class project. The mold consisted of 2 main parts, an inner core and an outer cope, and the space between them would determine the exact thickness of the bell's walls. Getting this spacing perfect was crucial because the wall thickness directly affected the bell's tone. Too thick, and the bell would sound dull and lifeless. Too thin, and it would crack under its own weight or produce a harsh, unpleasant ring. The inner core was built first, and it was essentially a solid clay replica of the inside of the bell. Workers mixed clay, sand, and organic fibers like chopped straw or animal hair to create a material that was strong enough to hold its shape but porous enough to let gases escape during the casting process. This mixture had to be just right. Too much clay, and it would crack as it dried. Too little, and it would crumble when they tried to work with it. Building the core was like constructing a sculpture from the inside out. Workers applied the clay mixture in layers, constantly checking measurements and smoothing surfaces. The core had to be perfectly smooth on the outside, because any imperfections would show up as bumps on the inside of the finished bell. This work required incredible patience because rushing could ruin weeks of preparation. One small mistake in the core meant starting over from scratch. The outer cope was even more complex. This was where the real artistry showed. The cope would create the outer surface of the bell, complete with all the decorative elements, inscriptions, and the crucial sound bow, the thickest part of the bell where the hammer would strike. Creating the cope required the wooden model to be pressed into the clay mixture, leaving behind a perfect negative impression. But here's where things got really tricky. The Japanese bell makers didn't just press the model into clay and call it done. They had to account for dozens of variables: the expansion and contraction of the clay as it dried, the way the bronze would flow during casting, even the way different parts of the mold would heat up at different rates. One master bell maker described it as trying to predict the future while working in 3 dimensions. The inscription bands were perhaps the most challenging part of the cope to create. These bands contained religious texts, dates, and sometimes the names of donors who had contributed to the bell's creation. Every character had to be perfectly formed and positioned. The craftsmen used special tools to carve these inscriptions into the clay, working with the precision of a surgeon. A single misplaced character could make the entire inscription meaningless, and there was no going back once the bronze was poured. The crown lugs presented their own unique challenges. These were the mounting points where the bell would eventually hang, and they had to be incredibly strong. The lugs needed to support the entire weight of the bell, sometimes several tons, while also being perfectly positioned for proper balance. If the lugs were even slightly off-center, the bell would hang crooked and never ring properly. The stress calculations required for these mounting points were remarkable, especially considering they were done without modern engineering tools. After both the core and cope were formed, came one of the most nerve-wracking parts of the entire process: the drying phase. This couldn't be rushed, no matter how eager everyone was to move forward. The molds had to dry slowly and evenly, or they would develop cracks that would ruin the casting. During winter months, this drying process could take weeks, with craftsmen carefully monitoring humidity levels and temperature changes. The drying had to be so carefully controlled that some workshops built special drying chambers with adjustable vents and controlled airflow. Workers would check the molds multiple times each day, looking for any signs of cracking or uneven drying. If they found problems, they had techniques for repairs, but every repair was a potential weak point that could fail during the intense heat of casting. Meanwhile, other members of the team were preparing for the most dramatic part of the entire process: melting the bronze. This wasn't just a matter of throwing some metal into a fire and waiting for it to melt. The furnace itself was a masterpiece of engineering, built specifically for each casting and then destroyed afterward. These weren't permanent installations, but custom-built furnaces designed to reach the exact temperatures needed for that particular bell. The furnace construction was almost as complex as making the mold. Workers built thick walls using special fire-resistant bricks and clay, creating a chamber that could withstand temperatures over 1100 degrees Celsius. The furnace had to be designed with precise airflow patterns to ensure even heating, and it needed multiple access points for adding fuel and monitoring the melt. Getting the furnace design wrong meant the difference between perfect bronze and expensive failure. The bronze itself was a carefully guarded recipe. The typical alloy was roughly 80% copper and 20% tin, but master bell makers often had their own secret variations. Some added small amounts of other metals like zinc or lead to achieve specific tonal qualities. The exact proportions were crucial because they affected not just the sound of the bell, but also its durability and resistance to cracking. Preparing the metal for melting was its own art form. The copper and tin had to be absolutely clean, free from any impurities that could weaken the final casting or create air bubbles. Workers spent days cleaning and preparing the raw materials, removing any traces of dirt, oxidation, or foreign metals. Even tiny amounts of the wrong materials could ruin a casting worth months of work and enormous amounts of money. The timing of everything had to be perfect. The molds had to be completely dry, but not so old that they started to deteriorate. The furnace had to be at exactly the right temperature. The metal had to be clean and properly proportioned, and the weather had to cooperate. High humidity or sudden temperature changes could spell disaster for the entire operation. It was like conducting an orchestra where every instrument had to play its part at exactly the right moment, and there were no second chances for mistakes. As the big day approached, the furnace crew knew they were about to play with forces that could kill them in seconds. We're talking about molten bronze at temperatures hot enough to melt copper pennies like butter. One splash of this liquid metal could burn through flesh and bone faster than you could scream. But these craftsmen treated it like they were making breakfast, calmly going about their preparations with the confidence that comes from years of experience and the knowledge that hesitation could be fatal. The smelting process began before dawn. The furnace had to be brought up to temperature gradually. Too fast and the walls could crack, too slow and they'd waste precious fuel. Workers fed the fire with carefully selected charcoal. Not just any wood would do. They needed charcoal that burned hot and clean, without the impurities that could contaminate their precious bronze. Some workshops had their own charcoal makers who specialized in creating fuel specifically for bell casting. Talk about attention to detail. Here's something that'll make you appreciate modern safety standards. These guys were working with molten metal while wearing nothing more than leather aprons and cloth wraps around their hands. No safety goggles, no heat-resistant suits, no emergency procedures. Just skill, experience, and probably a healthy dose of prayers to whatever gods watched over metalworkers. The lead smelter was usually a man who'd spent decades learning to read the color and behavior of molten metal like others read books. The copper went into the furnace first because it had a higher melting point than tin. Workers had to judge the exact moment when the copper reached the perfect temperature. Not just molten, but molten at exactly the right heat. Too cool, and it wouldn't mix properly with the tin. Too hot, and it would start to oxidize, creating impurities that would weaken the final bell. The experienced smelters could tell the temperature just by looking at the color and movement of the liquid metal. It was like having supernatural powers, except the superpowers were earned through years of burns, mistakes, and hard-won knowledge. Adding the tin was the moment of truth. The tin had to be absolutely pure and added at exactly the right rate. Too fast, and it would create turbulence that could introduce air bubbles. Too slow, and the temperatures would start to equalize unevenly. The master smelter would signal his assistants with hand gestures, calling for more tin or telling them to slow down. Communication had to be perfect because the roar of the furnace made shouting useless. But the real skill came in skimming the slag. As the metals melted and combined, impurities would rise to the surface like scum on a pond. This slag had to be removed constantly, but you couldn't just scrape it off carelessly. Removing too much meant losing good bronze. Removing too little meant impurities in your casting. The skimming tools were long-handled ladles and scrapers that allowed workers to reach into the furnace without getting too close to the deadly heat. The slag itself told a story to those who knew how to read it. Different colors and textures indicated different problems or successes in the melt. A greenish slag might mean too much oxidation. A chunky, rocky slag could indicate impurities in the raw materials. Master smelters could diagnose problems with their bronze alloy just by examining what they scraped off the top. It was like being a doctor, except your patient was a cauldron of liquid metal that could vaporize you if you made the wrong diagnosis. Testing the bronze was an art that bordered on insanity. Some smelters would dip iron rods into the molten metal and examine how the bronze behaved as it cooled on the rod. Others would pour small test samples into clay cups and crack them open to examine the internal structure of the cooled metal. The most experienced could even tell if the alloy was right by the sound it made when they stirred it with their tools. Different bronze compositions created different sounds when agitated, and a master's ear could detect variations that would escape everyone else. When the bronze was finally ready, the pouring had to happen fast. Molten bronze doesn't stay at the perfect temperature forever, and once it started cooling, there was no going back. The entire crew moved into action like a choreographed dance where one wrong step meant disaster. Workers positioned themselves around the gated runner system, a network of channels that would guide the molten bronze from the furnace into the buried mold. The runner system itself was an engineering marvel. These channels had to be designed to fill the mold evenly, preventing air pockets while allowing gases to escape through carefully placed vents. The main channel was called the sprue, and it fed into smaller channels that distributed the bronze around the mold. But here's the tricky part. The channels had to be sized perfectly. Too narrow, and the bronze would cool before filling the mold completely. Too wide, and the metal would rush in too fast, creating turbulence and air bubbles. The gates, the openings where bronze entered the actual mold cavity, were positioned with mathematical precision. Bell makers had learned through centuries of trial and error that bronze had to enter the mold from the bottom and rise slowly, pushing air out through the top vents. Pouring from the top seemed logical, but created disasters as the falling metal would splash and create air pockets that would show up as holes in the finished bell. The risers were even more clever. These were extra chambers connected to the mold that served as reservoirs of molten bronze. As the bronze in the mold cooled and contracted slightly, the risers would feed additional metal to compensate for the shrinkage. Without risers, bells would have sunken areas or internal voids that would ruin their tone. It was like having a backup fuel tank for your casting. The moment of the pour was absolutely electric. The furnace crew opened the tap hole, and molten bronze began flowing through the runner system like liquid fire. Workers monitored each gate and riser, watching for problems. If bronze started backing up in one channel, it might mean a blockage. If it flowed too fast through a gate, it could mean the channel had eroded and was now too wide. Every second counted, because once the pour started, stopping was nearly impossible. The sound was incredible, a combination of rushing liquid, hissing steam from any moisture in the system, and the deep rumble of the furnace. The light from the molten bronze lit up the entire workspace like orange lightning. Workers had to be constantly alert because molten bronze could spray or splash without warning. One small steam explosion from trapped moisture could send droplets of liquid metal flying in all directions. Watching the risers fill was like watching a slow-motion race. The bronze would appear in each riser at slightly different times, depending on the flow patterns through the runner system. When all the risers were full and overflowing slightly, the pour was complete. But that was just the beginning of the waiting game. The buried mold, now full of liquid bronze, at over 1,000 degrees Celsius, had to cool slowly and evenly to avoid cracks. The cooling process was perhaps the most nerve-wracking part of the entire operation. There was nothing to do but wait and hope. The mold was buried in sand or earth to insulate it and promote even cooling, but internal stresses were building as different parts of the bell cooled at different rates. The thick sections would stay hot longer than the thin sections, creating thermal stress that could crack the bronze if the cooling wasn't controlled perfectly. Some workshops had techniques for managing the cooling process. They might pack different materials around different parts of the mold to control cooling rates, or even light small fires near the mold to keep certain areas warm longer. The goal was to minimize the temperature differences within the cooling bronze, reducing the internal stresses that could cause cracks. Days passed with everyone holding their breath. Workers would place their ears against the ground near the buried mold, listening for any sounds that might indicate cracking. The bronze would occasionally make small popping or crackling sounds as it cooled and contracted, and distinguishing between normal cooling sounds and the sound of disaster required years of experience. The first sign that something might have gone wrong would be a dull thud from underground, followed by an ominous silence. That sound meant the bronze had cracked during cooling, and months of work had just become worthless scrap metal. But when everything went right, the only sounds were the gentle settling noises of cooling bronze and the collective sighs of relief from everyone involved. Temperature monitoring was done by touch and instinct. Master casters would place their hands near the buried mold, feeling for heat radiating through the earth. They could tell you within a few degrees how hot the bronze was just by the warmth they felt through several inches of soil. Some claimed they could predict exactly when the bronze would be cool enough for breakout just by the way the air smelled around the mold site. After what felt like an eternity, usually 3 to 5 days, came the moment everyone had been waiting for and dreading in equal measure. Breakout day was like unwrapping the world's most expensive and potentially disappointing present. Workers carefully excavated around the mold, removing layers of earth and sand with the delicacy of archaeologists. One careless shovel strike could damage the bronze surface that had taken months to perfect. The first glimpse of bronze through the cracked clay was either cause for celebration or immediate despair. Experienced casters could tell instantly if the casting had been successful just by looking at the surface quality where the mold had cracked away. Smooth, even bronze with a consistent color meant success. Pitted surfaces, color variations, or visible cracks meant problems that might or might not be fixable. Removing the mold material was painstakingly slow work. The clay and sand had to be chipped away piece by piece, revealing the bronze beneath like a sculpture emerging from stone. But here's the thing that would drive modern manufacturers crazy. They couldn't use power tools or compressed air. Every bit of mold material had to be removed by hand, using chisels, brushes, and endless patience. The runner system and risers had to be cut away first. These bronze appendages had served their purpose during casting, but now had to be removed without damaging the bell itself. Cutting through solid bronze with hand tools was brutal work. Workers used hacksaws, chisels, and files, taking turns because the physical effort was exhausting. The bronze was still harder than most metals they worked with regularly, making every cut a battle. Here's where the real artistry began. Once the rough casting was freed from its mold, the finishing work started. Every seam line where the mold pieces had joined needed to be ground smooth. These seam lines were like scars that revealed exactly how the mold had been constructed, and removing them required both skill and an artistic eye. Grinding too much would create flat spots that would affect the bell's tone. Grinding too little would leave visible marks that would mar the bell's appearance. The inscription bands required the most delicate work. Each character had to be cleaned and sharpened using tiny chisels and engraving tools. Religious texts that had been formed in reverse in the clay mold now appeared in readable form on the bronze surface, but they needed crisp, clean edges to be properly legible. One slip of the chisel could ruin an entire line of text, and there was no way to fix such mistakes in solid bronze. But the most critical part of the finishing process was something most people never think about: tuning. That's right, temple bells had to be tuned like musical instruments. The sound of a bell isn't just one note. It's a complex mixture of fundamental tones and overtones that have to work together harmoniously. Getting this right required both musical knowledge and an understanding of how bronze thickness affects pitch. The tuning process was like surgery performed with hammers and files. The inner surface of the bell's sound bow, the thick rim where the striker would hit, determined the fundamental tone. Removing metal from the inside of the sound bow would raise the pitch. Leaving it thick would keep the pitch low. But here's the crazy part. They had to make these adjustments without being able to hear the full tone until the bell was completely finished and properly hung. Master bell tuners developed an incredible sense of how much metal to remove. They would strike the bell gently while it lay on its side, listening to the partial tones it produced. By comparing these muffled sounds to their mental library of how bells should sound, They could predict what the final tone would be when the bell was properly mounted. It was like being able to tell what a finished painting would look like by examining the individual brushstrokes. The thickness variations across the bell's surface were crucial for proper tone production. The sound bow had to be the thickest part, gradually tapering toward the crown. But this taper couldn't be uniform. Different parts of the bell had to be different thicknesses to produce the right overtones. Some areas might need to be filed thinner to eliminate harsh overtones, while others needed to stay thick to maintain the fundamental tone's strength. Tuning tools were specialized instruments that looked more like medieval torture devices than musical equipment. Heavy files with coarse teeth could remove metal quickly from large areas. Smaller, finer files allowed for precise adjustments. Some tuners used scraping tools that could remove paper-thin shavings of bronze, allowing for incredibly fine pitch adjustments. The most experienced tuners could change a bell's pitch by fractions of a semitone just by knowing exactly where and how much to file. The real test came when they hung the bell for the first time. This wasn't just a matter of throwing a rope over a tree branch. Temple bells required specially constructed mounting systems that would support enormous weight while allowing the bell to swing freely. The crown lugs, those mounting points cast into the top of the bell, had to align perfectly with the hanging hardware, or the bell would hang crooked and never ring properly. The hanging system itself was an engineering marvel. Massive wooden beams formed the frame, joined with traditional Japanese woodworking techniques that used no nails or screws. These joints had to be incredibly strong, because they were supporting not just the weight of a motionless bell, but the dynamic forces created when the bell was struck and began to swing. A bell weighing several tons creates tremendous stress on its mounting system when it starts moving. The striker arrangement was just as critical as the bell itself. Most temple bells used a suspended log that would be pulled back and released to strike the bell. But the positioning of the striker had to be absolutely perfect. Strike too close to the rim, and you'd get a harsh, metallic sound. Strike too far from the rim, and the bell wouldn't produce its full volume. The sweet spot was usually about 1/3 of the way down from the rim, but this varied depending on the bell's specific proportions. Finding the perfect strike point required extensive testing. Workers would hang the striker at different positions and test the sound quality at each position. They listened not just for volume, but for the clarity of the fundamental tone and the balance of overtones. A properly struck temple bell should produce a sound that seems to grow in complexity as it fades, with different overtones becoming prominent at different times during the decay. The striker itself had to be the right size and weight for the specific bell. Too light, and it wouldn't produce the bell's full voice. Too heavy, and it could damage the bronze or create an unpleasantly harsh attack. The log was usually wrapped with rope or cloth at the contact point to soften the initial impact and create a more musical strike sound. Some bell makers experimented with different wrapping materials to achieve specific tonal qualities. But here's something that would amaze modern acoustical engineers. These craftsmen achieved all of this without any electronic measuring equipment. They relied entirely on their ears, their experience, and their understanding of how bronze behaved. They could tune a bell to specific pitch relationships, using nothing but their musical knowledge and hand tools. Some master tuners claimed they could predict a bell's final sound just by examining the thickness patterns in the raw casting. The first test strike was always a moment of supreme tension. Months of work, enormous amounts of money, and the reputations of everyone involved all hung in the balance. If the bell cracked on first strike, everything was lost. If it produced the wrong tone, weeks of additional tuning work lay ahead. But when everything went right, when that first strike produced a pure, resonant tone that seemed to hang in the air forever, it was pure magic. The sound of a properly made temple bell is unlike anything else in the world. The initial strike produces a complex burst of overtones that gradually separate and fade at different rates, creating an ever-changing harmonic landscape. The fundamental tone might sustain for minutes, gradually revealing subtle beating patterns as different overtones interact. It's a sound that seems to have physical weight, filling not just your ears, but your entire body with vibration. Testing the decay characteristics required patience that would drive modern engineers insane. Workers would strike the bell and then time how long different components of the sound lasted. The fundamental tone should sustain the longest, while the higher overtones should fade more quickly. But the pattern of this fading had to follow specific relationships, or the bell would sound harsh or incomplete as it decayed. The final tuning adjustments were made with the bell in its permanent hanging position. Even tiny changes in how the bell was supported could affect its tone, so all final work had to be done with the bell exactly as it would be used. This meant tuners had to work while standing on scaffolding or ladders, filing and testing in conditions that were far from ideal. One wrong move could send a heavy file crashing down onto the bell's surface, creating a dent that would permanently affect its sound. Weather conditions during testing were crucial, but completely unpredictable. Temperature and humidity affected both the bronze and the surrounding air, changing how the bell's sound traveled and how it was perceived by listeners. A bell that sounded perfect on a cool, dry morning might seem harsh and metallic on a hot, humid afternoon. Experienced tuners learned to account for these variables, testing their bells under different conditions to ensure consistent performance. The most challenging part of the entire process wasn't the casting, the tuning, or even the hanging. It was knowing when to stop. Every craftsman involved could always find something else to adjust, another surface to polish, another fraction of a semitone to file away. But overtuning could ruin a perfectly good bell, and knowing when perfection had been achieved required wisdom that came only from decades of experience and probably more than a few expensive mistakes. The numbers behind these incredible bells tell their own fascinating story. A typical temple bell from this era contained roughly 80% copper and 20% tin. But master founders guarded their exact ratios like state secrets. Some added trace amounts of silver for clarity. Others swore by microscopic quantities of gold for warmth. The wall thickness wasn't uniform either. The sound bow where the striker hit might be 4 inches thick, gradually tapering to just 1 inch near the lip. This wasn't random. Every millimeter was calculated to produce specific acoustic properties. The pouring temperature had to hit that sweet spot around 1100 degrees Celsius. Too hot, and the bronze would be turbulent, creating air bubbles that would ruin the casting. Too cool, and it wouldn't flow properly into all the intricate details of the mold. Masters could judge this temperature by the color of the molten metal and the way it moved when stirred. They developed an almost supernatural ability to read liquid bronze like others read books. Mass was everything when it came to sustaining power. The smallest temple bells weighed around 300 kilograms, but the monsters could tip the scales at several tons. There's a direct relationship between mass and how long a bell's tone will sustain. More bronze means more stored vibrational energy, which translates to those incredible decay times that could stretch for minutes. The largest bells were so massive that their fundamental tones were felt as much as heard, creating vibrations that would resonate through temple floors and into the bones of everyone present. The hanging systems had to account for forces that would terrify modern engineers. When a multi-ton bell starts swinging after being struck, it creates dynamic loads that can multiply the static weight by factors of 3 or 4. Those wooden frames weren't just holding up a heavy object, they were containing a massive pendulum that wanted to tear itself apart with its own momentum. Japanese carpenters developed joinery techniques specifically for bell towers, using interlocking wooden joints that could flex under stress without failing. Placement within the temple complex was almost as important as the bell's construction itself. The acoustic properties of the surrounding buildings, the materials used in nearby walls, even the landscaping around the bell tower, all affected how the sound would propagate and be perceived. Some temples were designed with the bell tower positioned to take advantage of natural amphitheater effects created by surrounding hills or valleys. Weather protection became a constant battle against the elements. Bronze might last for centuries, but the crown fittings where the bell hung were vulnerable to corrosion from rain and humidity. Temple keepers developed maintenance routines that involved periodic inspection and re-lacquering of these critical mounting points. They learned that a small amount of corrosion in the wrong place could change how the bell hung, which would alter its tone forever. The most remarkable thing about these temple bells wasn't just their initial perfection, but their longevity. Properly made and maintained, they could ring with crystal clarity for hundreds of years. Some bells cast in the 1600s are still in active use today, their bronze surfaces worn smooth by centuries of weather, but their voices as pure as the day they first sang. The craftsmanship that went into each bell represented not just months of work, but generations of accumulated knowledge about metallurgy, acoustics, and the mysterious relationship between metal, sound, and the human spirit. These weren't just functional objects. They were masterpieces of engineering that happened to make beautiful music. Every aspect of their creation, from the initial wooden pattern to the final hanging adjustment, represented human ingenuity pushed to its absolute limits, using nothing but fire, metal, and centuries of hard-won wisdom. And there you have it, 6 months of backbreaking work, centuries of accumulated knowledge, and enough skill to make modern engineers weep with envy, all coming together in that single perfect moment when bronze meets Stryker and produces a sound that seems to come straight from heaven itself. These Japanese bell makers weren't just craftsmen. They were masters of an art form so complex that we're still trying to figure out how they did it. Think about what we just witnessed. No computers calculating optimal bronze thickness. No electronic tuning equipment. No temperature sensors or stress analysis software. Just human hands, experienced eyes, and ears that could detect the difference between perfect and almost perfect with supernatural precision. These guys were pulling off acoustic engineering miracles with nothing but clay molds and hand tools. The most mind-blowing part isn't even the technical achievement. It's the fact that many of these bells are still ringing today, 4 centuries later, sounding exactly as pure and haunting as they did when they first sang. That's not just good craftsmanship. That's immortality cast in bronze. So the next time you hear any bell, church bells, wind chimes, even your doorbell, remember the incredible human story behind that simple sound. Months of planning, weeks of dangerous work with molten metal, and generations of knowledge all focused on creating something that will outlast empires and still bring beauty into the world long after we're gone.